Hello, we are going to take a look at some practice problems in your book in Chapter 6, Section 5, and do some examples. All right, we're going to start with the practice problem number 1 on page 403. So the reaction shown occurs in the atmosphere when oxygen oxidizes the pollutant factory exhaust, sulfur dioxide. What volume of oxygen is required to oxidize the 2.41 times 10 to the 7th liters of sulfur dioxide released annually by a coal-based power plant at STP? So we've got sulfur dioxide plus oxygen. The sulfur dioxide is what's released from the power plant, adds to the oxygen already in the air, and it makes sulfur trioxide. So we want to know what volume of oxygen we are producing. So we're focusing in on oxygen. We want to know how many liters it has. And we are oxidizing 2.41 times 10 to the 7th liters of sulfur dioxide. So we have liters of sulfur dioxide. So we need to convert from one to the other. So we're going from liters of one to liters of the other. It is at STP. So we do have permission to use our 22.4 liters per mole. So to get from liters of our sulfur dioxide, first we want to change it to moles. So we're going to use our molar volume. I'm going to put MV there. That's the 22.4. We do need to change our chemicals. So we're going to go to moles of oxygen. And then we need to get to liters of oxygen. So again, we're going to use that molar volume. So we're actually going to use it twice here. So we'll see how that works out with our values. So we have 2.41 times 10 to the 7th liters. It is in scientific notation, but we're not going to let that bother us. We just treat it like a number. And that is our sulfur dioxide. We're going to copy those units to the bottom, and we want moles of sulfur dioxide. So we're going to use our 22.4 liters per mole because it is at STP and it is a gas, so we can use that. And we're going to cancel out our liters of sulfur dioxide. Then we're going to copy our units to the bottom, moles of SO2, and we want to change to moles of O2. Our mole ratio we get from the coefficients on the balanced reaction. So our coefficient on SO2 is 2, and oxygen is 1, and that allows us to cancel moles of sulfur dioxide. Last, we want to again copy those units to, all right, so moles of O2, at the bottom, and we're going to liters of O2 on the top. So again, we're going between moles of liters. It's at STP and it's a gas, so we're going to use that 22.4 liters per mole again. Now here's the interesting thing we can notice here is that we have this 22.4 twice. And really it's being divided by itself. So we could reduce that or ignore those numbers because it's dividing by itself and it would be 1. So that happens when we have gases at STP. And we've got gases for both of our chemicals. So it simplifies our math. So we've really got 2.41 times 10 to the 7th divided by 2. So we end up with, excuse me, oh goodness, 1.21 times 10 to the 7th liters of oxygen. Always good to check in your calculator, make sure you're getting the same number so you get that practice in on your calculator. All right, let's try another one. So the exothermic reaction to potassium plus water forming potassium hydroxide and hydrogen often releases enough heat to ignite the hydrogen gas it produces. What mass of potassium metal would be required to produce 250 milliliters of a 0.45 molar solution of potassium hydroxide? So if we take potassium and throw it in water, it actually creates a lot of hydrogen gas. It gets super hot, and because it gets so hot, it can ignite the hydrogen gas, which is very flammable. So it's actually a pretty dangerous reaction. So we don't do it in class. So we're looking for mass of potassium metal. So that's going to be our solid potassium. And we are producing 250 milliliters of a 0.5 molar solution of potassium hydroxide. So those are our two chemicals we're looking at. In this case, we are given a molarity. So this is kind of not new because we have looked at molarity, but kind of a different viewpoint of it. instead of just looking at it in the context of that one chemical, now we're relating it to the whole reaction. But we are also given a volume of that. Now, because our molarity has moles per liter, it's telling us the ratio between the moles and liters of that solution. That means we can use this for the molarity for a conversion. Okay, it's not our starting number. Our starting number is going to be our volume of it that's measured out. So we have 250 milliliters of that potassium hydroxide solution. Now, in order for us to use this molarity, we need to get those milliliters to liters. So we're going to go ahead and just do that real quick, just so our numbers are in liters, our units are in liters. So 1 liter is 1,000 milliliters. So that just gets rid of our milliliters, and now we're in the unit we want. Now, let's kind of set things up. We've got liters of potassium hydroxide. We're going to need to get to potassium, so we're going to have to change this to moles and then do a mole ratio to get to potassium. And our potassium, we want grams of that. So we're going to have to do 3 more conversions here. Now, this conversion, the first one, to get from liters to moles of the KOH, that's where we're going to use our molarity. So let's see how that works out. We want to get rid of liters of KOH. We want moles of KOH. Now, we know based on the molarity, it is 0.45 moles per liter. Now, that allows us to change between those moles and liters. So we can use that molarity for a conversion. So this is our molarity. We're only going to be able to use that molarity for aqueous solutions, okay, because those are the only ones that have a concentration. It's something dissolved in water, so we get that concentration. All right, let's keep going. We can bring down those units, copy them to the bottom. Our map says we want to change our chemical to potassium. So our ratio here is just 2 to 2 from our coefficients. That's pretty easy for us. In terms of our math, we can really ignore it. And then our last step, we want to get it to grams of potassium. Potassium's molar mass is 39.10 grams per mole. So now we're going to calculate. So we've got 250 times 0.45. I'm going to go ahead and put the 2 in there, times 2 times 39.10, divided by 1,000, divided by 2, because those are both on the bottom of our equation. So we end up with 4 point, and I'm going to check my sig figs. I've got 2 sig figs on my given value, so I'm going to round to 4.4 grams of potassium. So if I take about 4.5 grams of potassium and throw it in some water, 250 milliliters of water, I will get a 0.45 molar solution of potassium hydroxide, but potentially a fire hazard as well. Now let's try another one. Okay, so this one, it says what volume of 0.8 molar sodium iodide solution. So we can see we're given a molarity again, and it's sodium iodide, so that's going to be this one. Oh, this is a typo. That should say aqueous there. Sorry about that. Would completely react with 2.4 times 10 to the 24th molecules of chlorine gas. So we are looking at chlorine gas. We have molecules, and we want volume or liters of our sodium iodide. Now we are also given that molarity of sodium iodide, so we can use that to get from moles to liters of that. Now we're starting at molecules of chlorine. We're going to have to change that one to moles and then get to our other chemical using our mole ratio. So there's our steps. Now, we want to take a second and think about molecules. Think to yourself, which conversion or tool might you use to get from molecules to moles? So hopefully you thought of Avogadro's number, which is what we're going to use. Avogadro's number, remember, is 6.022 times 10 to the 23rd, is on your equation sheet. And on there, it is often confusing for students because it says moles to the -1. Okay, so most of the time I see students, when they set up a conversion, they'll put 6.022 times 10 to the 23rd, oops, 10 to the, oh my gosh, And they'll put, instead of putting the moles in the right place, they'll put moles with it, like that. And then they don't know what to write here. So let's fix this problem. Your 6.022 times 10 to the 23rd, when it says moles to the -1, that's like putting your moles on the bottom. So it's per mole, okay, when we're setting up those ratios. This can be flipped either way, but those two things are separate from each other. What units go with this, with Avogadro's number, are whatever you're counting. So if I had a mole of donuts, it'd be 6.022 times 10 to the 23rd donuts per mole. Okay, if I had a mole of, atoms, then we'd write atoms here, right? In this case, we're counting molecules. So that's the unit that's going to go with Avogadro's number. Okay, so let's go ahead and start setting up our equation. Molecules is not great in terms of abbreviations. I use MOLEC, and we're going to do in Cl2. So we want to go from molecules of chlorine to moles of chlorine. Again, those are not the same thing. Be very aware of that. A molecule is not the same as a mole. A molecule is an individual unit, like Cl2. Those two things bonded to each other. A mole is 602 hexillion of those. Okay, different things. So in 1 mole, we have 6.022 times 10 to the 23rd molecules. That is our ratio. That allows us to get rid of molecules and leaves us in moles. We can copy that to the bottom. We want moles of NaI, sodium iodide. And our coefficients are 2 and 1. So we can get rid of our chlorine, moles of chlorine. We want to go from moles of sodium iodide to liters of sodium iodide. And this is where they give us our molarity. So we have 0.80 moles per liter of sodium iodide. All right, so we're using that molarity to change our moles to liters. And now we can calculate. So we're going to do 2.4 times 10 to the 24th. Remember that we want to use that E button on our calculator for our times 10 to the power. We're going to multiply by 2 and then divide by Avogadro's number and divide by 0.8. Okay, so we end up with 9.96. So we're going to have to round that. That would round to 1. That would round to 10. So yeah, so we'd have 10 with a decimal liters of sodium iodide solution. So we'd have 10 liters of sodium iodide solution, and so that solution is 0.8 molar. Okay, I think we've got one more example. So let's check out this one. Again, using a couple of tools that we haven't seen used together before. So we're looking at how many liters of carbon dioxide, let's go ahead and box that, we're looking for liters, would be formed at STP. So I have permission to use, I'm going to just write STP here. So I can use my 22.4 to go from between liters and moles to do that conversion. If 1.5 liters of 1.75 molar phosphoric acid, acids have hydrogen in the front, and that's basically hydrogen phosphate. So phosphoric acid, we have liters of it, and we have a molarity that can allow us to find moles. It says we're reacted with excess potassium carbonate solution. We know this is excess. That means we have plenty of potassium carbonate to make this reaction work. So we want to change liters of our phosphoric acid to liters of carbon dioxide. Now, one is an aqueous solution where we use molarity to convert, and one is a gas at STP where we use 22.4 to convert molar volume. Okay, so this is seeing both of those used together. So we've got 1.5 liters of H3PO4 And we're going to go ahead and change those liters to moles. All right. So we use our molarity, which is 1.75 moles per liter, and that allows our liters to cancel. Now we want to change those moles of phosphoric acid to moles of carbon dioxide gas, what we're looking for. And in this case, it's a 1-to-1 ratio, so that one's pretty straightforward. And that allows us to cancel the moles of phosphoric acid. We bring down our moles of carbon dioxide, and we want liters of carbon dioxide. We know that this is at STP, so we can say 22.4 liters per mole of carbon dioxide. Cancel out those units, and we can calculate. So this one's actually a pretty straightforward calculation. So 1.5 times 1.75 times 22.4, we get, let's see, we have 2 significant figures here. We are given a second value with 3 significant figures. Because we have 2 givens, we want to go with use the one with less significant figures, so we go with 2 sig figs. Okay, so our answer we end up with should be 59 liters of carbon dioxide gas. So this one is interesting because we are using liters for both chemicals, but in different contexts, because one is liters of liquid volume, one is liters of gaseous volume. So paying attention to those states of matter is really important, and what it's giving you there, how we break these down. So the homework to go with this is all of the section review for 6.5, skip number 13, and then I have posted on Teams and handed out in class all of the chemical reactions that go with numbers 6 through the end, which I think is like 20, yes, 6 to 20. So all of those have their chemical reactions written, so you have that to refer to. That is given to most of the time on your AP test, so that you have your chemical reaction. The other thing I will also point out with a lot of these, or a couple of these examples, number 1 and 3 from this page, it gave you liters and molarity, and then asked about another chemical. That is the most common way that I've seen it used on the AP test. They love to give you liters or even milliliters and molarity, and you have to use those at the beginning to find moles. So that's a really good step to know how to do, to get really used to, and this will help this practice, okay? Have a great day, guys.